So far in this topic, we've looked really at the idea of ionizing radiation, where a nucleus will uh, split and decay and give out alpha or beta or gamma radiation. But there's another part to this topic, which is looking at nuclear energy. So there's energy stored in the nucleus of an atom that can be released that we could exploit, usually by powering a power station to generate electricity. And there are two main processes. There's nuclear fission and nuclear fusion. And we need to know the very basics of what does fission mean, what does fusion mean. We need to know what sort of fuels are used, what nuclei are involved in the process, and some of the advantages and disadvantages. Firstly, nuclear fission. Nuclear fission is the process by which all nuclear power stations in operation today use. You've already looked at energy resources. You know that fossil fuels, for example, are used to, you burn the fossil fuel, you produce heat, which can boil water, make steam under high pressure. That can turn a turbine and can then turn a generator. Nuclear fission uses exactly the same process once the heat is produced. It's just a process by which uranium fuel is used to produce heat, which can make steam and so on. The fundamental thing to remember about nuclear fission is that it involves the splitting of a heavy nucleus into two lighter nuclei. So we need to start off with a very heavy nucleus, and the ones that we normally use are uranium-235 or perhaps plutonium-239. So we have a heavy nucleus, and something happens that causes it to split into two smaller nuclei and release something else. We've said that radioactivity is spontaneous and random. We cannot make it happen. This is a slightly different thing. Uranium-235 by itself is radioactive, but it's not going to split in half. However, if it is struck by a neutron and absorbs that neutron, it becomes less stable and will split into two roughly equal halves. Not exactly equal, but roughly equal halves. That splitting releases energy in the form of heat. Now, by itself, that's not very important, but what is important is that as well as splitting into two smaller nuclei, it can produce some extra neutrons, and that's where we get something called a chain reaction. So, in this process, we have a neutron. The neutron is absorbed by the uranium-235, which becomes unstable. It splits into two smaller nuclei and also ejects extra neutrons. Those neutrons can go on to be absorbed by other uranium-235 nuclei, causing them to split, and in turn giving out more neutrons. And on and on and on the process goes. One splitting uranium nuclei will result in 2 or 3 more splitting, which will result in 8 or 9 or however many more. And this is known as a chain reaction, where one reaction causes the next, causes the next. Left uncontrolled, this would be disastrous. It would result in an explosion, and that is the process behind some nuclear bombs. In a nuclear power station, this is controlled by absorbing some of the extra neutrons and slowing down the chain reaction. So, important thing to remember, the fuel is uranium-235, which is a heavy nucleus. It absorbs a neutron and splits into smaller nuclei, releases further neutrons, and those neutrons will cause the fission or splitting of other nuclei, and so on. The waste products that are left behind, there's a variety of them, but they're nearly all very radioactive, and some of them are radioactive for a very, very long time. And that's one of the major disadvantages of nuclear fission, and we'll see this later on in your notes. One of the major advantages is we're producing heat, but without having to burn anything, so there's no carbon dioxide produced, so it does not contribute to the greenhouse effect. Another advantage is there's an awful lot more energy released by fission than by burning. So a small mass of fuel can produce the same amount of energy as a very large mass of coal or oil. We'll look at some more of the advantages and disadvantages in our notes later. The second process we want to consider is nuclear fusion, and this is the power supply for the sun. and all other stars. And it works very differently from nuclear fission. Fission had a large nucleus that splits into two smaller ones. Fusion is the joining of two very light nuclei into a heavier nucleus, and with that releasing energy. The problem with this is normally nuclei are positive and will repel each other very strongly. The closer they get together, the stronger that force of repulsion. To get this to work, we need incredibly high temperatures to move the nuclei fast enough so that they can collide. These temperatures in the order of hundreds of millions of degrees Celsius. On Earth, all the nuclear fusion reactions that take place are in experimental fusion reactors. And the most common reaction involves fusing hydrogen-2, an isotope of hydrogen with one proton and one neutron. This is known as deuterium. With hydrogen-3, or tritium, which is one proton and two neutrons. These isotopes can be found in water, or hydrogen-3 can also be produced from lithium. And so that we have a plentiful supply of these fuels, an almost unlimited supply, which is one of the major advantages. The deuterium and the tritium are smashed together at incredibly high temperatures and will reform into helium, two protons and two neutrons, and an extra neutron is given off as well. Helium is non-toxic and has no real side effects. It just floats off into the atmosphere, so it's a non-harmful waste product. Neutrons by themselves can be dangerous. However, they can be absorbed in systems inside the reactor and can be used to actually regenerate some of the tritium fuel. And a neutron by itself only has a half-life of about half an hour, so they won't stay around for long. There is some radioactive waste produced, but dramatically less than nuclear fission. So the major advantage of nuclear fusion is we have an almost unlimited fuel supply with very little harmful waste. The major disadvantage is it requires temperatures of hundreds of millions of degrees to contain this process and to start it. That will vaporize any material, so it has to be controlled in a magnetic bottle. Hugely strong magnetic fields are used to control the plasma, and the temperature has to be increased enormously. It's very hard to get these conditions stable on Earth. In a system like a star, there are huge gravitational forces which aid, but we don't have access to that on Earth. The formula for nuclear fusion is deuterium plus tritium turns to helium plus a neutron plus energy. You can see in the same way as we had to balance the mass number and atomic number of a decay equation, the mass number and atomic numbers balance here. On the left hand side 2 plus 3 is 5, on the right hand side 4 plus 1 is 5. For the atomic number 1 plus 1 equals 2 plus 0.